Good day and welcome to today's class. In our last class, we talked about operations on set, where we start with the union of set. Okay, so today we want to consider another operation under the set theory, which is known as the intersection of set. Okay, so we start by defining what intersection of set is. Okay, so we first of all start with two sets, after which we generalize uh, for more than two sets. Okay, so let's see the definition. The intersection of two sets A and B in the universal set is defined by A intersection B. So this symbol that looks like a cap is a symbol for intersection, and when we have this, we say this is equal to the set of elements X in U. Okay, so you will recall in our last video that anytime we have a universal set U, okay, so this universal set U has some subsets. So in this case, the subset of this U are A and B in this case. Okay, so if you are looking for the intersection of these two sets, okay, so it will be the element in U. Okay, so together with the following property, such that X is an element in A and X is an element in B. So this sign is a conjunction sign under the logic, and it has been used to define the intersection of two sets. Okay, so what we are saying literally is that the intersection of two sets is this set is the element X in U, such that X is an element in A and X is an element in B. So unlike the union of two sets where the property says X is either in A or X is in B. Okay, in this case it has to be and. Okay, this means that X has to be in A and must be in B at the same time. Okay, so the set of elements that satisfy this property are what referred to as the intersection of the set. Okay, so let's see an example before we make a further clarification of what the intersection of sets are. So example, given the universal set U equal to 1, 2, 3, 4 up to 8, and then the set of elements in the U is 1, 3, 4, 5, then 6, and B is equal to 2, 4, 6, 8. Obviously, both the set A and B are subsets of U. Okay, so if you are now asked to find the intersection of A and B, okay, we'll recall that by definition, okay, this has to be the element in A and B. Okay, so by so doing, we'll start, okay, from A and see the elements that are in A and also in B. Okay, so 1, if the first element is 1 here, 1 is in A but not in B. Okay, so meaning 1 is not an intersection of the two sets. Let's consider 3. 3 is in A and 3 is not in B. Okay, so this means 3 cannot be the element in the intersection. Okay, the next number 4 is in A and 4 is in B. Okay, so the first element of the intersection is 4. Also, we have 5 here. 5 is in A and 5 is not in B. Okay, so 5 is not a member. So also 6 is in A and 6 is in B. Okay, so this means 6 is a member. Okay, so this is the result of the elements that are the intersection of these two sets. Okay, so having said that, it is possible to have intersection of two sets. Okay, and then at the end we have no element. So if this arise, okay, so we say that the two sets are disjoint. Okay, so there is no notation for this. So let's quickly see that after this. Two sets A and B are said to be disjoint if A intersection B is equal to an empty set. Okay, so in this case, okay, we say A and B has no common element. Okay, so we can use this notation to represent an empty set, as we have said in our previous video, or we can use this symbol phi. Okay, so let's see an example of this. Okay, for example, so if you are given A to be the set of odd numbers and B is a set of even number from 2 to 8. Okay, then A intersection B has nothing in common. Okay, and this is because there is no element that are in A and B. Okay, so if you pick one is in A but not in B, 3 is in A but not in B, 5 is in A but not in B, 7 is in A but not in B. So it means no element to pick. Okay, so this means A and B are disjoint. They are disjoint. Otherwise, if they are not disjoint, okay, we say A and B is not equal to an empty set. Okay, otherwise, okay, we say A and intersection B is non-empty. So like the first example, okay, satisfies this condition. Okay, so now let us see from the special numbers the intersection of two special numbers. So suppose A is equal to the element x such that x is a member of the rational number, and B is a set x such that x is a member of the irrational number. Okay, so as we have said in our previous example, this set contains set of rational numbers and this set contains set of irrational numbers. Okay, so in this case, A intersection B, okay, is disjoint. Okay, is disjoint. Okay, so these are how we make use of the intersection of two sets. So we cannot generalize this concept of intersection into more than two sets. If A1, A2 up to AN are sets in the universal set U, okay, so then you can see this is in general the intersection of A. Okay, so we can generalize the intersection of all these sets as this, and this simply means A1 intersection A2 intersection up to the last set, which is AN. Okay, and this is nothing but equal to the set X in U. Okay, the set the elements that are common to the set A1, A2, A3 is a set in the universal set such that X belongs to A1 and X belongs to A2 and okay up to the last element, and X belongs to AN. Okay, so any element in the universal set that satisfy this property, okay, so are element of the intersection of this set. Okay, so this is not far-fetched, okay, to see. Okay, so having said this, let us now look at some properties of intersection of sets. So let us now see some properties on intersection of sets. Again, we want to consider three sets A, B, and C. So to be the universal set, to be the set in the universal set, so then one, if you take the intersection of AB, this is similar to intersection of B and A. Okay, and we refer to this as the commutative law. Okay, so A intersection B is the same thing as B intersection A. Just like in algebra, we have commutativity under addition and multiplication. That is, under the addition, if you pick any two numbers, 2 and 3, 2 plus 3 is the same thing as 3 plus 2. Okay, likewise, in the under the multiplication, you can say 2 times 3 is the same thing as 3 times 2. That's commutative under the algebra. Okay, in like manner, this is commutative law under the set theory. Okay, so number 2, under the associativity, this law shows that is, if you are to group the intersection of A and B, the intersection C, this is similar to the intersection of A, B, okay, intersection C. Okay, we refer to this as the associative law. Associative law. Okay, also, it is possible for us to have identity under the intersection. If you take the direction of the set A and the universal set U, this is the same thing as the set A. Okay, and we refer to this as the identity under the intersection. Okay, so 4, we can also have the intersection of a set, okay, of itself. Okay, this is equal to A. If a set intersect itself, okay, we'll have that set. Okay, and we refer to this as idempotence. Okay, so you will recall we have the similitude of this in under the union of two sets. Okay, so and the fifth one here is if you have the intersection of a set and the empty set. Okay, if a set A intersects the empty set, of course, both of them has nothing in common, and because of this will be empty, and we refer to this as the boundary law on the band law. Okay, so these are some of the properties we have for the intersection of sets alone. Okay, so since we have discussed the union of set earlier, okay, so there are a way to link up the union of sets and that of the intersection of sets. Okay, so this will now bring up another law, which we know as the distributive law. Okay, so we can state that under this. Okay, that okay, so let's continue this number. Okay, but we should know that the next law here combine both the union of set and the intersection of sets. Okay, in this case, we'll consider 3 sets. Okay, A union B intersection C. Okay, so this will be equal to A union B intersection A union C. Okay, this is we refer to this as distributive law. Okay, so but there are 2 kinds of them. The second one is intersection B union C is similar to A intersection B union A intersection C. Okay, so these 2 law are referred to as the distributive law. Okay, so we can either take any of this law, which is referred to as the absorption law. Okay, There are two types of this also. Okay, this is if you have A union A intersection B. Okay, this will give us A. Okay, and then the ninth one says if you have A intersection A union B. Okay, this is also A. Okay, and we refer to this as absorption law. Okay, so this is how both the union of sets and the intersection of sets, okay, are used together. Okay, so in our next class we look at another concept called the set difference, the complement of sets, and the symmetry difference of a set. Okay, but before then, say bye for now.